Hi everyone, this video is about the INCH project of AI planning for autonomy, presented by the group 27. In this strategy board game, we are aiming to have our agent remove 3 of our own rings before the opponent based on the game rules. We tried 3 different techniques to complete the task, which are the depth first search as the blind search agent, the greedy best first search and alpha beta pruning as the heuristic search agents, and the Monte Carlo tree search agent. First of all, the depth first search as a blind search algorithm is easy to implement and requires short computation time in practice. However, without considering the situation on the game board, it doesn't really choose a good action in most cases. Then we implemented a greedy best first search agent, which takes advantages of both breadth first search and depth first search. With proper heuristic design, it can provide much better performance. The depth first search agent in green seems to be moving randomly around the board, while the GBFS agent in purple is trying to form a line and remove rings. However, both of these algorithms are not optimal. Next, let's welcome Yalin to introduce the alpha-beta pruning agent.
Thanks, Jingwei. Next, let me briefly introduce the alpha-beta pruning implementation. In the case of an exhausting search on the huge space of the game board, we implemented the alpha-beta pruning to decrease the number of nodes that evaluated by minimax algorithm, and it can increase the search depth twice in the same amount of the time. The initial alpha is negative infinity as the max value, and beta is infinity as the minimum value, which were updated by the max or minimum value from each trial node. For example, when our own agent is at the max layer, the value is calculated based on the max value of each trial node, and the value of the state at the next layer is calculated in the opposite way, because we expect opposite player will move with the least value to us. However, the limitations still exist. We need to limit the search depth at 2 to keep time, and the optimum solution is not guaranteed to be found. Meanwhile, the timeout still happens very often. To solve this, we implemented BVS to only explore the nodes with an alpha and beta value window, and also try to combine iterative deepening to increase the search depth. Here are the demo alpha-beta compete with the other agents. On the left-hand side, alpha-beta flip over the opposite counter to get score. On the right-hand side, alpha-beta occupy the corner position to get scores in the early stage. Next, Xiaochen introduce MCTS agent.
For the last part, I'm going to talk about our agent selected for the final tournament. It's called MCTS Greedy Line. It adopted the Monte Carlo tree search, and we made some changes to its reward system to get better performance for the game INCH. The reward is calculated based on the difference of max number of counters in a line comparing 2 players, and the rings won are counted as 10 to appeal the agent to form a line of 5. To illustrate this, on the right hand side, there is a screenshot representing state of game, so 24 points for teal, 23 for magenta. Teal is the winner at this stage, and the reward is difference 1. To invent a new reward system, we need to have a better understanding of the game INCH. We tried a number of ideas before to get the reward effective and practical. If we have more time on this project, the next optimization is to find out the optimum value for C parameter that's used in UCB1 for balancing the exploration and exploitation. We have done some research saying square root of 2 is the best value for the reward in the range of 0 to 1. We tried this by normalizing the reward, but it didn't go well. Here's a clip of MCTS Greedy Line playing with alpha-beta pruning. We can see that the teal or green player is lining up above the magenta, but who is 1 county behind. Magenta is now in a line of 4, about to form a sequence. The MCTS gave up what it was doing and cutting off the magenta line. What a brilliant move. That's all for the presentation. We are Team 27. Thanks for listening.